The value of this aluminum alloy part, when installed in place on an airplane, rests on its physical and chemical characteristics. Through heat treatment, these characteristics can be improved to produce a part which, although it has the same appearance as before, is stronger and harder and better able to meet the demands of an airplane in flight. It can stand up to the forces tending to fracture it by compression. It can resist forces acting in tension upon it, tending to fracture it by stretching. It can repel the forces tending to bend and break it. And it can more successfully resist corrosive attack by the elements. Heat-treated and non-heat-treated parts look no different from each other. Since changes in physical and chemical properties do not strike the naked eye, they are measured indirectly by testing instruments and studied by examination of alloy specimens under the microscope. The changes in the metal's properties are reflections of changes in the metal's internal structure. An understanding of the aluminum alloy's crystal grain structure, shown in this photomicrograph, is essential to an understanding of the heat treatment process and its accompanying property changes. Crystallization occurs in the initial production or casting of aluminum and aluminum alloys and is the physical root of the metal's characteristics. As the molten metal is cooled to its freezing point, groups of atoms join together at various points throughout the liquid to form small individual lattices or unit cells of solid material. The single lattice or unit cell is conceived to be cube-shaped, with atoms of the metal arranged in regular order, one at each corner and one in the center of each face of the cube. Aluminum unit cells are classified as the face-centered cubic type. The axes of these unit cells are oriented or aimed at random in many different directions. Each crystal formation expands and becomes a larger unit known as the grain. In growing, adjacent grains make contact, interfering with the free growth of the outermost cells. These cells, sheared and broken during growth, give the grain its jagged and irregular shape, although the body of the grain is regular and crystalline. It is the grains and their boundaries that constitute the network structure shown in the photomicrograph of an aluminum alloy specimen. Within the lattice-type pattern produced by the combination of unit cells, atoms of the metal exist in families of parallel planes with definite spacings between planes. It is along certain planes of weakness, called slip planes, that gliding or slipping may occur when the lattice structure is subjected to a load. The plane along which slip is most likely to occur is generally the one with the greatest atomic population and the largest spacing between it and its parallel neighbor. These are important slip planes, along which movement may take place in the aluminum crystal. The process of slip or deformation of the metal begins with application of a load or force and the distortion of the lattice structure under that load. When the load exceeds the elastic limit of the metal, blocks of the crystal lattice begin to slide over each other. Upon removal of the force, The elastic stresses in the individual blocks are relieved, but the lattice structure remains deformed. Continuance of the force beyond the metal's ultimate strength would result in rupture or failure of the metal. To strengthen the metal, alloying elements are added. Further strength may be gained through heat treatment of the alloys thus formed. The aluminum alloy consists of two main types of metallic combinations. The first is the solid solution of the alloying element in aluminum. The atoms of the alloying element are dispersed throughout the aluminum, displacing some of the atoms in the aluminum crystal lattice. The second is the formation of an intermetallic compound between the alloying element and the aluminum. In the case of alloy 24S, the compound formed by copper with aluminum is copper aluminide, or CuAl2. As temperature is increased, the alloying element becomes increasingly soluble in the solid aluminum. The solubility of copper in solid aluminum increases from 0.5% at 392 degrees Fahrenheit to 6% at 1040 degrees Fahrenheit. In actual heat treatment practice, care must be taken to stay well below the melting point of the alloy or any of its constituents. Prior to heat treatment, the alloy 24S contains relatively large, undissolved particles of the copper aluminum compound CuAl2 scattered unevenly throughout the mass of the aluminum. In the solution stage of the heat treatment process, temperature is increased and the CuAl2 particles decrease in size as the copper gradually goes into solid solution with the aluminum. Subjection of the alloy to the proper temperature for the right length of time brings about the disappearance of the CuAl2 particles. The copper has now been largely dissolved in the aluminum. The solid solution is now retained or captured by a quick quench, which provides rapid cooling of the alloy. However, at room temperature following the quench, fine submicroscopic particles of CuAl2 begin to precipitate out of solution and to disperse evenly throughout the metal. These particles represent the copper brought into solution at higher temperatures and which the aluminum is unable to retain in solution at room temperature. Many of these precipitated particles are distributed along the slip planes or planes of weakness. In these locations, the particles serve as keys or props which secure blocks of unit cells in position and interfere with slippage. This is the most generally accepted explanation of the increase in the metal's hardness and strength as a result of heat treatment. The extent of change in physical properties may be judged by testing the aluminum alloy before heat treatment in the S condition and after heat treatment in the ST condition. One of these is a test for hardness, generally conducted on a Rockwell hardness tester. A penetrator is applied to the specimen with a fixed load, and the depth of penetration is taken as an indication of hardness. Another test is for resistance to corrosion. The solution potential test provides voltage readings which are a measure of this property. A third is a test for tensile strength. This measures the force required to fracture the metal in tension. The first stage in heat treatment procedure consists of a heating operation followed by a quick quench of the alloy part. Two different types of heating and quenching equipment may be employed in this process. The alloy part may be heated in an air furnace or in a salt bath furnace. Rapid cooling of the part may be accomplished by means of a spray quench booth or a quench tank. Parts to be heat treated must be properly racked to minimize their tendency to sag at elevated temperatures and to reduce warpage during the quench. Sufficient space should be allowed between parts to promote free circulation of the heating medium and later of the quenching water. The loaded rack is now ready to be placed in the furnace. Operation of the furnace is guided by automatic temperature and time controls. A thermocouple unit keeps the temperature within the range prescribed for a given alloy. The proper heat treating range for aluminum alloy 24S lies between 910 and 930 degrees Fahrenheit. The automatic timer is set to cover the proper heating time or soaking period. This will vary with the thickness of the alloy and its composition. For example, an alloy 24S part 1/8 to 1/4 inch thick should be kept at heat treating temperature for a minimum of 60 minutes in an air furnace. After the furnace has been heated up to heat treating temperature, it is ready for loading. The furnace door is raised pneumatically or hydraulically. The rack containing the alloy parts is rolled into the furnace, and the furnace door is lowered as quickly as possible. The two essential characteristics of an air furnace are rapid circulation of air and controlled heat. These are achieved by forcing heated air among the parts and maintaining nearly uniform temperature by controlling the heating elements. During the soaking period, the microstructure of the metal is altered, the CuAl2 particles growing smaller as the copper goes into solid solution with the aluminum. When the soaking period is completed, the operators prepare to remove the load from the furnace. The water is now turned on in the quench booth. The rear door of the furnace and the adjoining door of the quench booth are raised simultaneously. The rack is pulled out of the furnace and into the spray quench booth. The transfer from furnace to booth should be as rapid as possible, taking no more than a few seconds. Delay in transferring the load reduces the corrosion resistance of alloy parts. The load of alloy parts is quenched by the cold spray for a period of several minutes. The water accumulates at the bottom of the booth and is carried away through drainage pits to be used over again in quenching. The microstructure of the metal now shows most of the copper dissolved in the aluminum. The quick quench captures or holds the solid solution in this condition. After a load is removed from the furnace, an inspector checks the pyrometric control record to make sure that the load has been within heat treating temperature limits throughout the soaking period. Use of the salt bath as well as the air furnace requires correct racking of parts and setting of controls. After this has been done, the load is heated in the salt bath. At the end of the soaking period, the alloy parts are rapidly removed from the bath, transferred to the quench tank, and immersed in the cold water. The parts are then rinsed in the rinse tank, where the salt is washed away. Both quench tank and spray booth operations may cause distortion of the alloy parts, resulting from the swift drop in temperature. Hand hammering of the parts may be employed at this point to remove much of the warping caused by the quick quench. In aging, some of the copper precipitates out of solution in uniformly distributed particles of fine submicroscopic CuAl2. In the case of alloy 24S, precipitation occurs at room temperature, about 70 degrees Fahrenheit, and is practically complete in 1 day. Certain alloys age very slowly at room temperature. To speed this process, they may be reheated in an air furnace. For example, alloys 53S and 61S are aged at a temperature of from 315 to 325 degrees Fahrenheit for a period of from 12 to 18 hours. Through refrigeration, age hardening may be retarded in order to keep parts soft enough for forming operations. For example, by refrigerating 24S rivets, their driving characteristics may be retained for several days. If we take sample tests of the properties of a typical aluminum alloy 24S part in the ST or heat-treated and aged condition, we will obtain a measure of the improvement in the metal's physical characteristics as a result of heat treatment. We might find, for instance, that the tensile strength of the aluminum alloy part has risen from 30,000 pounds per square inch to 60,000 pounds per square inch. We may find that the Rockwell hardness number of the part has increased from H80 to H112. And we would also find that the alloy's resistance to corrosion has increased, as shown by a change in solution potential test reading from minus 0.710 millivolt to minus 0.670 millivolt. Thus, solution heat treatment has affected a desirable change in the physical properties of an aluminum alloy by controlling the size and distribution of the particles of the alloy constituent.